It's an opportunity for me to speak to people I haven't normally spoken to on my speaking circuit tours, so this will be interesting, and I hope we can all learn something. Hopefully I'll learn a lot from you guys. So I want to talk about topological methods for unsupervised learning, and the details of all of this are in the paper. I'm, in this talk, going to focus much more on motivation and intuition to just try and give an idea of where I'm coming from. So just to start with, let's make sure we know what unsupervised learning problems I'm wanting to address here. So the first sort of major topic is dimension reduction and visualization, where we're wanting to reduce data's dimension for machine learning purposes, or just to be able to visualize high dimensional data more easily. And the second sort of unsupervised learning problem I want to tackle is clustering and its sort of partner, anomaly detection. Okay, so just to start, let's talk about dimension reduction. So let's just ensure everyone's on the same page here. The problem is to find the latent features in your data. So what does that mean? Here's the first 100 entries of the MNIST digits data set, which hopefully some of you are familiar with. These are 28 by 28 pixel images of handwritten digits. And when you unwrap that 28 by 28 pixel thing into a vector, you end up with these 784 dimensional long vectors. And 784 dimensions feels like many more than you would need to adequately describe this data set. So the question is, can we find the sort of latent underlying features that describe this data set well that are much fewer than 784? A second test data set, just to give, because I'll be giving some examples. This is fashion MNIST. It's meant to be a drop-in replacement for MNIST. It's again 28 by 28 pixel grayscale images, but this time it's of fashion items. So shirts, dresses, footwear, and so on. Okay, so just to see what standard dimension reduction does on these sorts of things, this is principal component analysis of the MNIST digits data set, where I've colored the points according to which digit class they belong to. So you can see it's captured a lot of the overall global structure, but it really hasn't separated the individual digit classes very well at all. Here is PCA on that fashion MNIST digit data set I showed you. Again, we've got the overall global structure up the top there. You can see it's got the footwear sort of separated out from everything else. But again, you're not separating the digit classes. On the other hand, a very popular technique is TSNE, and here's TSNE on the MNIST digits data set. This time we've gone the other way around. We've really done a fine job of pulling out that class structure and grouped everything very cleanly, but we've lost a lot of that global information. Alternatively, on fashion MNIST, we can see that TSNE is not perfect because these class structures are really hard. The difference between various t-shirts and pullovers and shirts are hard to pick apart, so there's some class structure there that's a little messed up. But again, we mostly pulled out the classes really well, but we lost a lot of the global structure. Okay, so what would a topologically driven solution to dimension reduction look like? Well, here's a really toy data set just so we have something to work with, and the classical approach would be to use something like the nerve theorem to build a topological representation of the data and then go from there. So what would that look like? Well, we'd build a cover of the data with open balls, and then we'd basically take the nerve of that cover, which is going to build a simplicial complex out of that. It would look something like this, just using the nerve theorem. Now, this looks like it's capturing a lot of the information of that data. We've got the topology sort of, but it's not perfect. And the question is, why is it not working as well as we would like? Well, it comes down to some details in the nerve theorem and when it's applicable, but ultimately the answer is our data didn't look like this. This is uniformly distributed along that sort of notional manifold that I was drawing in there, and this would have worked perfectly. This would have perfectly captured the structure if you'd taken the nerve of that. So our problem is that our data is not uniformly distributed. So let's cheat and declare that our data will be uniformly distributed. Of course, real data never behaves like that. So what that means is we have to do something else. So what we're going to do in practice is try and define a Riemannian metric on the manifold that's going to make that assumption be true. We're going to have to vary our notion of distance across the manifold in a nice way so that the data is uniformly distributed with respect to that notion of distance. So we'd end up with a cover much more like this, where each of these balls is a unit ball with respect to whatever the manifold metric now is, rather than the ambient metric. So we're trying to get away from the ambient metric here. The catch, of course, is that I have discrete data points. I don't have the full Riemannian metric in a nice functional format, I just have local patches where I can locally estimate that. And each of those local patches and estimations are going to be a little local metric space, which is going to be incompatible with all the others. So how do we manage to glue all that information together to actually extract the real manifold information there? Well, I'm more from a category theory background, so my natural instinct is to take colimits, and of course the problem here is that colimits of metric spaces are hard to get, which is to say they don't exist. So let's steal ideas from algebraic topology to make this easier. So the classical idea in algebraic topology is that there are these two functors, the singular set functor and geometric realization functor, and they allow us to go back and forth between topological spaces and simplicial sets. Simplicial sets are nice and easy to work with. We'd like to work there. So can we get a similar thing? Well, there was a great paper by David Spivak which actually put together a nice approach where you can go back and forth between metric spaces now, but instead of simplicial sets, we get fuzzy simplicial sets. A fuzzy simplicial set is really just a simplicial set where the whole thing is a fuzzy set. If you don't like fuzzy set language, it's really just a simplicial sheaf, and that's actually how I tend to think about it, but fuzzy simplicial sets make it easier for some people. Okay, so we can adapt that to the finite case that we have and get a usable adjunction of functors there. It's going to be not especially tricky formula here. The details of this are not that important, but what it means is that we can then glue all these local fuzzy simplicial sets together using colimits. What I mean? Well, I said this is really a simplicial sheaf, and colimits of simplicial sheaves are pretty easy to calculate once you work through the details. So we can do all of that, and now we can glue everything together. We've translated it from a problem we couldn't solve over to a different realm using a bit of algebraic topology style machinery, and now we can solve this problem using colimits, glue everything together. Okay, so that's great. We now have a fuzzy simplicial set representation of the data. How do we turn that into a low-dimensional representation of the data? Well, how do we find a low-dimensional representation of a fuzzy simplicial set? That's ultimately our question. So, assume we get given some representation in a low-dimensional space. We could initialize that randomly, or we could find some smarter way to do it. At the end of the day, what we want to do is be able to say, how close is that representation, when we take its singular set, compared to the colimit we glued together. So we can measure that difference, at least to a first approximation, by looking at the cross entropy of the one skeletons. So the one skeleton of a fuzzy simplicial set is going to bring it back to a nice easy thing. That's just a graph where the edges have a probability of existence. And if that's an easier way to think about it, that's great. So all we're really doing with this cross entropy is we have essentially two terms where we're going to pull things together wherever edges have high probability of existing and push things apart wherever these edges have a low probability of existing. And that's all we're really doing. So that sounds nice in theory. Does it work in practice is a perfectly valid question. So here's that approach applied to the MNIST digits data set, and you can see we've managed to get some of the strengths of both TSNE and PCA out of this. From a TSNE point of view, we have successfully captured the individual classes really cleanly, but we also captured a bunch of the global structure. The ones and the zeros are at opposite ends of things, just like PCA produced, and you can see there are sort of groups of digits that are similar to each other. The 3s, 5s, and 8s, and 7s, 4s, and 9s are little triples that sort of group together as classes that are somewhat similar to each other, quite distinct from something like a 1 or so on. All right, how about fashion MNIST? Again, we get the same sort of results we had before, where we've pulled out the separate classes very cleanly, but we've also managed to bring in some extra information, like the fact that footwear is fairly disjoint from everything else. This was not something TSNE managed to pull out. Okay, so moving on, can we do something with clustering? Well, let's describe clustering first. There's really not any good descriptions of clustering because there are a lot of definitions of it, but the guts of it is just find the natural groupings within the data. So here's one test data set we're going to look at. Here's another. These are nice two-dimensional test data sets so that we can see what we're doing and see what clustering is doing. So just quickly going through the classics of clustering. Here's k-means on that first data set. It's doing quite a good job. Here's k-means on the second data set. It's doing a pretty awful job. Another popular algorithm, density-based clustering, dbScan, does okay on the first data set, could really do better. It's clumped things together more than it probably should have, but it's doing a far better job on the second data set than k-means, but still not perfect. Okay, so that's our background of what clustering looks like. What would a topologically driven solution to this look like? Well, what do we mean by a cluster is the first question we have to ask ourselves when we do clustering. And by cluster, I want to mean a connected component of the superlevel set of the probability density function of the underlying and unknown distribution from which the data samples were drawn. Okay, so what that means is we ultimately want to understand this probability density function from which the samples were drawn. So our assumption here is that the data is distributed on the manifold according to some probability density function. This time around, we don't want to make it all uniform. In fact, because of noise in the data samples, would actually like to do the opposite. So we're going to define a Riemannian metric that preserves or emphasizes the distribution rather than making it uniform. So this is really what we were doing for dimension reduction, just really in reverse, and that'll come through even more later. So each metric space is going to be incompatible with all the others, as we had before, but we already know how to deal with that. We can convert to fuzzy simplicial sets. As I said, we're doing the reverse of what we were doing last time, so instead of taking colimits, we're going to take categorical limits, which are really solving a system constraints in a sense. And now here's a toy data set to sort of see what this is going to look like. The one skeleton of the fuzzy simplicial set we get out would look something like this. So you can think of this again as a graph where the edges have a probability of existence. The darker the color, the higher the probability of the edge existing. And if you're staring at that, thinking that we've actually managed to get some notion of the probability density function from which this data was drawn, you're right, we have actually done a non-trivial job of capturing the topology of that probability density function. Ultimately, those higher density areas are more connected by higher dimensional simplices, is really what's going on. So what we're ultimately, at the end of the day, interested in, though, is the connected components. And fortunately for us, that all of a sudden gets straightforward in this model. We're working with simplicial sheaves. So post-composing with pi naught, the connected components functor turns a fuzzy simplicial set into just a fuzzy set of connected components. It just goes through naturally. It's one of those weird things. And so we can then sort of sort the points according to the range in that fuzzy connected component set. And you can pull out the clusters from that in a really straightforward fashion. There are a lot of ways you could go about doing this. There's excessive mass-based methods, there's information theoretic methods, there's persistence-based methods, but really they all pretty much give you the same thing, and this is what they give on that really toy data set that we were looking at, which are the clusters you were probably looking for when you first saw that data set. Okay, so I skipped through a lot of details there. There's more in the paper, but there's still a lot more to fine-tune in all of that. That was more of a sketch, but how does it work in practice? Well, here it is on the first data set, and you can see it's done a better job than dbScan of pulling out the clusters. Much more similar to k-means. There's some of the gray points that it's declared as background noise. That's okay. And then on the second data set, it's done really a remarkable job of pulling out what I think were really the clusters that were there in that data originally. So we have a great dimension reduction algorithm, and now with pretty much the same theory, we've pulled out a very, very powerful clustering algorithm. Okay, what about anomaly detection? Well, the guts of anomaly detection is just find the stuff that doesn't belong. So again, we need some test data sets. Here's one, here's the other. These are just simple data sets that we can just have a look at. The sort of standard approach would be a Dirichlet processed Gaussian mixture model. That would give something like this, where the more red the point is, the more it considers it an outlier. And you can see it's done a really good job of the very dense areas, but some of these other more sparsely grouped areas, it's still calling sort of fairly outlierly. Similar on the second data set, it does a really good job of the dense areas, but the rest of it, less good. Another very popular outlier detection algorithm is local outlier vector. It's much more conservative. Only a few points are declared outliers here. And again, on the second data set, much more conservative. The very, very outlierly points are definitely declared outliers, but everything else has a little more trouble with. Okay, So what would a topologically driven solution to outlier detection look like? Well, what constitutes an anomaly? A sample that is extremely unlikely to be observed given the unknown probability density function from which the data was drawn. But that means we just want to understand that probability density function again, and our clustering solution already did a lot of the heavy lifting of how to get that organized. So let S be that fuzzy set of connected components we got out of the clustering. We can remove any connected components that are below some reasonable threshold size. It's just too small to be considered useful. And then, for any point, consider the maximal value for which that point is in any connected component. And this represents the likelihood that the point is locally connected to the manifold as a whole. So that really is an outlier score, and it's a probability value. So it's a meaningful, interpretable outlier score as well. It's essentially the probability that this point is in any connected component of the manifold. How does that work in practice? Well, here's that proposed method, and you can see it's got some of the strengths of both local outlier factor and Gaussian mixture models. We do a better job in this region in the middle there, down here, where those are considered less outlying than Gaussian mixture models, but at the same time, we managed to declare more points more outlierly than something like local outlier factor was managing. Again, similarly with the other data set, we're doing a mixture somewhere between those two options I presented at first, some of the strengths of both coming through. So, in conclusion, these topological methods have a lot to say about actually very practical unsupervised learning problems. And what we've managed to put together here with just a bit of basic topology for the guts of it is a relatively good, somewhat unified theory for a good chunk of unsupervised learning. But there's a lot more we can do. There's a lot more unsupervised learning problems to solve, and there's a lot more details and fine-tuning that could easily be filled in with these algorithms. These were ultimately, at the end of the day, only sketches, even if many of them actually been implemented and are working in practice. There's still a lot more we can do with them. So thank you.